So we've been learning about factoring polynomials, and from that we've been able to factor and solve equations that we were not able to before, like cubic equations, quartic equations, quintic equations, and as high up as we want to go. And we've done that by factoring using the factor theorem, finding the zeros, using synthetic division, and then dividing all the way down to a quadratic equation. So if we have a cubic equation, we find one factor, we factor that out, then we have a quadratic equation, and then we can use a quadratic formula for that. But we've been getting those factors by people coming up and nudging us and say, hey, try 3 and see if that's a factor. Hey, try 4, see if that's a factor. Hey, try 7, is that a factor? We want to come up with a system where we can find the factor without people nudging us in the side and hinting and winking at us. So what we're going to do is we're going to talk about this system where we come up with a pool of numbers. What this is going to give us is, let me pick a color. It's going to give us some pool of numbers. Let me just explain the basic idea of what we're going to do. We're going to use the rational zero theorem, and what it's going to do is going to give us a pool of numbers from which the zeros must be present. All zeros will be present. Pool of numbers where all rational zeros are present. So once we have that pool of numbers, we then use the factor theorem. To find out if it's a root or not. And we kind of just use brute force, but at least we've narrowed down our possibilities to where it says it can only be these. It's kind of like it's like a police photo shoot. It's like when they bring in a bunch of guys and the suspect says, well, we know one of these guys did it, we just don't know which. And then we just test and find out which one it was. So that's the general idea of it. We come up with a pool of numbers that where all the zeros are in. We don't know which of these numbers it is, but we can use our factor theorem to figure out which one of those numbers it is. Because if we factor it and we get a remainder, then it's not a factor. So remainder, that's crappy. So if we get a remainder, it's not a factor. If it divides evenly, it's a factor. So now that we know what we're trying to accomplish by learning this theorem, let's talk about what it is. So let's read this. If a function, so this is just the standard form of a function, an xn plus an minus 1 xn minus 1. This is just some arbitrary function. So if some arbitrary function where each coefficient is an integer, if pq in lowest terms is a rational zero of f, then p must be a factor of a0 and q must be a factor of an. And if you don't know the proof of this, then this means absolutely nothing to you. But that doesn't mean that we still can't learn how to use it. And I'm not going to do the proof of this in this video. I will attach the proof as a response to this. Because I understand that a lot of people don't really care much for proofs, and they just want to get the answer, especially if you're trying to become an engineer or something like that. But it is helpful to know, and actually it's a very nice proof. I found it very pleasing to solve. So if you want to see it and understand why it's P and Q, you really have to look at the proof. But we can still learn how to use this. What this is basically saying is that if there is a zero, so if there is a rational zero, it's equal to P over Q, where P is a factor of a0. So a0 is the constant, and q is the factor of an, which is the leading coefficient. So let's write that down here. It's pq, where p is factor as constant, factor, coefficient. And if you want to know why it's the constant and coefficient, you'll have to look at the proof again. But regardless, we can still learn how to use this. So, a rational zero is the ratio of p to q, where p is a factor of the constant, and q is a factor of a coefficient. It has to be. And it's more apparent in the proof, so, I mean, it's kind of annoying to have to, I don't know. I kind of want to go over it, but I'm not going to right now. So anyways, so what this is saying, that if there is a zero, it's got to be a factor of the constant divided by a factor of the coefficient. So what we can do to find out what these are is let's take an example. This will be easiest to explain with an example. Let's say I have 2x cubed plus 5x squared minus 4x minus 3. See, this is what it's going to give us our pool of numbers. We know that if there is a rational zero, that it has to be a factor of the constant divided by a factor of the coefficient. But, as we see over here, there are more than one factor. Alright, let's look. This is a factor of the coefficient, and this is the factor of the constant. So const and co. So let's write out the factors. So the factors of the constant are, so for minus 3, the factors are plus and minus 1 and plus and minus 3. And it's plus and minus because we can have positive 1 times minus 3, or we can have positive 3 times minus 1. So it's going to be plus or minus. And the factors of 2 are plus and minus 1 and plus and minus 2. And the same reason, because for positive 2 we can have minus 1 times minus 2, and we can have 1 times 2. So according to this theorem, it's saying that the zeros have to be factors of the constant, so these divided by these. So here we have multiple possibilities. So what we do is we come up with a pool of numbers. So what's basically happening is, here are our constants, and here are our coefficients. And in order to come up with a pool of numbers, we need to write out all possibilities. So we can have plus or minus 1 over 1. We can have plus or minus 1 over 2. We can have plus or minus 3 over 1. And we can have plus or minus 3 over 2. These are all the possible zeros. We can have, or let's simplify them. But you can see what I've just done. These are these are all the possible combinations of a factor of the constant over a factor of the coefficient. We know it's one of these, or it could be multiple of them. Any possible zeros will be here. We just don't know which one. So we have to write out all of the different possible combinations. And then from these possible combinations, we can then start testing with our factor theorem. So the points to test are, or the zeros to test are, plus and minus 1, plus and minus 1/2, plus and minus 3, and plus and minus 3 over 2. And we have to test each one of these independently. So these are all the possibilities of P over Q. A factor of the constant and a factor of the coefficient. We don't know which one of these it is, but it has to be one of these if there is a zero, or more than one. All the zeros have to be in this pool of numbers. And now the way we find out if this is a factor is by using our factor theorem. We're just going to use synthetic division and see if it divides in evenly. So let's set up some synthetic division. Let's do -1 first. So we have 2, we have 5, -4, and -3. I believe, yeah, 2, 5, -4, -3, yeah. So if this is a factor, so if -1 is a factor, it will divide evenly. If it is not a factor, it will not divide evenly. So let us begin. So 2 times -1, this is -2, this brings us to 3, -3, this gives us -7, this gives us +7, and this gives us 4. So we have a remainder of 4, so this is not a factor. So let's try 1 now. So 1, we still have 2, 5, -4, and -3. So let me move down a little bit so we can not get confused. So now we're trying 1, because this is plus and -1. We have to try plus and -1, plus and -1/2, plus and -3, plus and -3/2. But we only really need to find 1, because then we can divide out and use quadratic formula. So we have 2, 5, -4, and -3. So let's begin our synthetic division. We have 2, 1 times 2 is 2. So we have 7, 1 times 7 is 7. 4 minus 7 is 3. 1 times 3 is 3. And then we have 0. So this is a root. So x minus 1 is a factor. And not only that, we've already divided out. So when we divide this equation by x minus 1, we've already got we've already done all the work, so we don't have to do that again. So this is the constant, this is x squared. So this is the same as, so here's our original function. Because it divided evenly, this is a factor. So our original function is 2x cubed plus 5x minus 4x minus 3. And what we've just done is we've just taken out x minus 1. So this is equal to x minus 1 times this. 2x squared minus, or plus 7x plus 3. But not only that, we can simplify this more. I just wanted to show that all we've done is just factored out x minus 1. But we can also simplify this more. We can use quadratic formula, or we can just look at this and factor. Say 2 times 3, that's 6. So what will that give us? That'll give us, say, x minus 1. That'll give us 2x plus 1. It's x plus 3. And I've just factored this just by I, because I can just multiply it, and then we got 6, and then we had two numbers. So 6 and 1, so yeah, 6 and 1, and then 2, so that's 3. But we can use quadratic formula. I just didn't feel like taking up a bunch of time. But often we'll have things that don't factor. So this is the same as this. We've just factored it out. And we can see all of the zeros. We can see that x is, so when x is equal to 0, so x minus 1 is equal to 0, if x is equal to 1, we have 2x plus 1 is equal to 0, so that gives us 2x is equal to minus 1, x is equal to minus 1/2. We have x plus 3 is equal to 0, and x is equal to minus 3. So we have minus 3, 1, and minus 1/2. And if we go back up to our pool of possible zeros, we see we have minus 1. We have minus 1. Oh, wait, I mean 1. So we had minus 1/2, 1, and minus 3. So we have positive 1. So we can see that's in our pool. We can see we have minus 1/2. And we can see we have minus 3. So we can see that all the possible zeros were there. And we had all these other ones that weren't there, but at least all of our zeros were there. So that's what the basic idea of this theorem is this theorem finds us the pool of possible numbers, and from there we're able to just test those randomly until we get enough zeros to where we're able to get down to a quadratic equation and use a quadratic formula.